Okay, let's start. Good morning and welcome back. So in the last lecture, we were discussing about the need for non-linearity to get power amplification. And there were some questions even during the class and even after the class. So let me quickly revisit the concept, then we'll move forward. So what did we say? We have a voltage source. Let's say it's Vp sine omega t. And we have a load RL. So we want to generate some voltage on RL, right? We want to generate some voltage on top of RL such that the power delivered to RL will be more than the power that I'm extracting from the source. So in order to do that, obviously we'll have to put some network here, to insert some network. All we are interested in is the property of this network. Is there any particular property of this network that will help us realize the same? Then we saw that, from argument it came out that only this contraption will not suffice because the power that is going in will be more than the power that has come out, simply because it's passive, right? Passivity will ensure, or rather enforce, that you cannot deliver higher power than whatever you are taking in, right? So then we said that, okay, which means I probably will need another power source. Let's stick out another power source. And let's call it VDD, which is typically the battery we use in our everyday life. And let's see, what are the consequences of this? So note that this is an LTI system, right? This is still an LTI system. We started off assuming that this network N is an LTI. So if this is an LTI, how do I go ahead and analyze this contraption? I can use the only property of LTI that is of use in this particular example is that of superposition. And what is superposition? I can say that the output here is a combination of the case when VDD is equal to 0 and when the source Vp sine omega t is equal to 0, right? And I can add them both up. Add each of their responses as if the other one was null. And that essentially is what superposition is. So here, if we say that what we get is alpha Vp sine omega t plus beta VDD, where obviously alpha and beta are characteristics of the LTI network N. So now, if I redraw how we got this, so how did we get this? We will see that in order to get this electrically, or if you have to do an experiment, this is how we will proceed. So you'll take this port, short it, and you will apply Vp sine omega t here. You will get alpha Vp sine omega t. And in experiment 2, you will short the input. Apply VDD. And what should you get at the output? Beta times VDD. Great. So superposition essentially means that whatever I get after each of these two individual unrelated experiments, I can add up the outputs, and the final output will be as if both the input sources were there in the first place. Okay. So now let's impose passivity. Let's impose the condition of passivity under this constraint. Okay. So I'll come to that. Alpha and beta will be less than 1 if under certain conditions. So let's look at it right away. So what does passivity tell you? Passivity essentially tells you that power in and power out are related. And what essentially we see is power out has to be less than power in, right? So in order to figure out what is power in or power out, I mean, I did it in an ad hoc manner in the last class. Let's go into a bit more rigor. So if I have to figure out what is power in, I also need the information on what is the current going in, right? So let's assume the current going in is IP sine omega t. And you can have IT to IP sine omega t plus phi. I mean, in general, it should be, it's a phasor, so it's not necessary that the phase of the voltage and the current need to be matched, but without loss of generality, let's assume this is how it is at the moment, right? So whatever we will do following this will not depend on whether they are in phase, out of phase, or sine omega t plus phi, as in, right? Okay, so what is power in? Power in, or rather, what is power out? Power out is alpha squared Vp squared by twice RL, right? By the way, what is the frequency of the output? Frequency at which I'm observing the output? Omega, right? So this is, we say that this is the power P out at omega, right? So there were some questions again about what do you mean by power of frequency of a power. So when we say frequency of a power, we essentially try to convey that what is the frequency of the signal at the output, and ultimately what is the power conveyed by that particular signal, what is the power carried by that particular signal. So in this case, the signal is at omega. I am calculating the power of that signal. So even though you have done a squaring operation, it doesn't mean that the signal frequency has changed. Since the power is conveyed by the signal, is carried by the signal, we are saying that the power out at omega is whatever it is, alpha squared Vp squared by 2R. So what will be power in? P in will be Vp IP by 2. Right? These are all average powers. When I say power, power essentially means average power, unless it's specifically told that it's instantaneous power. By definition, power is average. You don't have to put that bar on top. Okay, so now what passivity tells us? Passivity is telling us that alpha squared Vp squared by 2RL is less than Vp IP by 2. Okay, so this is the condition that is imposed, which means alpha squared is less than IP by 2 Vp times RL. Okay, so this is the condition imposed by the passivity. Now alpha will be less than 1 if there is a certain relationship between IP and Vp, right? So that's coming back to your question, but it need not necessarily be alpha should be less than 1. Yes. Oh, sorry. Yeah, correct. Thank you. So yes. Okay. So if you put in, look at this network. So if you apply a voltage, you will draw a current, and current will be at the same frequency or different frequency? Same frequency. It will have an amplitude, some frequency, and some phase, right? I'm assuming the phase is 0 because not important for this discussion. So IP is the amplitude of the sinusoid that is going in. Okay, fine. So if we agree on this, then let's go back and find out the Right. The point of the circuit is to increase the power. What we are trying to get at here is that can an LTI circuit do that? Right?
Why did we put P out less than P before the mechanical? It won't work as well.
Okay, there is no point even going there, right? Because in this, if we consider this network, this is okay. So when you say admitting, what do you mean? Can an LTI, or rather, forget about LTI, can a passive network give you higher output than an input power? So this statement is essentially that. This statement is essentially that. I mean, this is fundamental, right? This doesn't depend on the network. You can have whatever inside the 10. This statement is true. It has to be true, right? Correct. So alpha will be, so yeah. So I understand what you are saying now. So what you are trying to say is that why do I put this condition? Why am I trying to figure out alpha here? This whatever P out will get, alpha will be a function of. True. I agree. So the reason I want to do it is I'll put back the condition when I do superposition. Right. So when nothing has changed. Right. Okay. So if now I am trying to go back to this original circuit, and will try to convince you that given the conditions that we have just derived, you will not be able to get power gain, even if you have two sources in conjunction. Right? So let's do that. Yes.
Power as linear, because explaining what power is position of alpha and beta VD. But here you are seeing it as sine of power and VD of
Correct. But note that I am not finding out the power of these two circuits together. This constraint is coming because as if almost this was not there. Right? So note that this alpha will not change if I put this VDD back. Right? Superposition, linearity. That's what I am trying to drive, right? So essentially now, I mean, if you follow this discussion, even the discussion I am having with you, what's your name? Atman. Right. So the discussion that I'm having with Atman, I mean, the next step is even obvious. I'll not have to even write it out. Because what essentially is said that, see, I am putting VDD back. I mean, why am I, this condition of alpha does not need to be valid because his contention is that, hey, I am putting VDD in. So this powered out less than powered in should not be valid in this case because I am getting I am getting total higher power. It seems like I can get higher power because I have two sources. I can get higher power than I would have gotten it with a single source. That's essentially your contention.
So that practice condition
Right.
obtaining by individually seeing circuit and inequality that will be obtaining by circuit as a whole. They both
Right. You are right, but there comes the trick. The trick that comes here is that when you put them together, each of the ratio with which the term on omega and the term with zero frequency will get scale will not change because of superposition, because of linearity. Right? So that's what we'll see when we do the combination stuff, right? When we'll put these together. What will I get at the output? I will get alpha times VP sine omega t plus beta VDD. So without going into the detailed maths, what will be P out? Alpha squared VP squared by twice RL plus beta squared VDD squared, right? So note that by the condition imposed here, by the condition, forget about this condition. You don't even have to look into this condition. By the condition imposed here, so by the way, even I'm jumping ahead. So this power is carried by the frequency of a sinusoid at omega, and this power is being carried by a frequency of sinusoid 0. By RL, right? Thank you. So what do I want? I want the frequency, I want the power at omega to be higher than the previous case, right? But as you see, even if I am putting in a battery of VDD, the output is still the same, right? Superposition, right? So I'm not benefiting. I'm not really benefiting by adding a battery. I'm benefiting in terms of total power, but I'm not benefiting in terms of the power at omega, right? Does that make sense? Okay, so now why am I not benefiting? It's basically because I'm not being able to transfer the power from the battery, which is operating at 0 frequency, to a sinusoidal frequency of omega. So which essentially means that I need some sort of frequency translation. Okay, so one way to do that is that even if you go back to trigonometric expansions, if you let's assume a generic nonlinear circuit, and generic nonlinear circuit N, and you have a VDD. This is nonlinear. Now note that in a nonlinear circuit, you cannot use superposition, which means you will have to analyze this in conjunction. So let's say that this nonlinearity is of some form. You have to assume some form. Let's say simplistic form is that you have a linear combination and you have a square combination, right? So let's assume your V naught is some alpha times Vp sine. This alpha need not be same as the previous alpha. It can be anything. Plus beta VDD plus, let's say, a combination of alpha Vp sine omega t plus beta VDD whole square, right? You can go cube and so on, cube and to the power 4 and so on, but this is sufficient to make the point. So now what I'll do, I'll expand and collect the terms of omega 0 and whatever else remains, right? So what will I get? I'll get sorry, this is V dot squared, right? VDD squared plus 2 alpha times VDD times sine of omega t. Okay. So if I collect the terms of sine omega, what do I get? I get these two together. So you can already see what's happening. Vp plus bunch of DC terms plus I'll get one extra term at 2 omega because sine squared term gets converted to 1 minus 2 cosine. So this becomes beta alpha squared Vp squared by 2 cosine 2 omega t. So now note that simply because you have a nonlinear system, you are getting, there is no surprise that we'll get a DC term that we are getting earlier also. You have a DC source, you've got a DC term. But let's concentrate on this, the amplitude of sine omega. So in the absence of nonlinearity, you were only getting this. In the presence of nonlinearity, you are getting an additional term, which is this. And note that this term is proportional to VDD. Right? So in principle, I can crank up VDD to whatever value I want at DC. VDD is still at DC. I can crank it up to whatever value I want to get this amplitude of sine omega to be as high as I want. right? So if I can do that, essentially I'll be able to get a power amplification. And this is happening because you have a squaring operation happening. Yes.
Can we say that the DC sources also can also produce AC current with the AC source?
Right. It cannot simply produce. It has to go through that multiplication operation. And then multiplication is being facilitated by the nonlinearity. Right? Some sort of multiplication operation has to be there. Okay. So that is why there is another class of systems which is not a part of this course. We call that linear time varying systems, where linearity is valid, but your time invariance is not valid. There also you will see you can have multiplication operation. That's linear but multiplicative. So in those cases also you can get frequency translation. But again, I mean, as for the purpose of this course, let's limit ourselves to linearity and to non-linearity. So as you can see that it's possible to increase the amplitude of the sinusoid at the frequency of your interest by simply getting a curated nonlinear source, the nonlinear system, and another battery. Yes.
So will that be always of the form eta alpha Vp sin omega t plus beta VDD square, or can it be gamma Vp sin omega t plus delta VDD square?
I didn't understand the question.
In the second term in the VD. Is it always of the form eta into the alpha?
Okay, it can be anything. I mean, I just took a random nonlinearity. What you are saying is that can there be another gamma here? There can be, right? And this, I mean, there can be gamma there, whatever, zeta somewhere. It can be anything. The point is not that. The point is not the coefficients. The point is the fact that you are able to translate VDD from. So type of nonlinearity depends on the coefficient will depend on the type of nonlinearity. So any good old nonlinear circuit will not be able to give you power amplification, because this gamma, beta, eta are not proper, not appropriate, right? So the whole purpose is to use those circuits where these nonlinearities are appropriate. But beyond that, what I would like to emphasize is that this is a scenario where I could demonstrate. I hope you are convinced that a translation of VDD is possible from zero frequency to a desired frequency if you have a nonlinearity in the system. Okay. Now, directly from this expression, you see that sure I am getting power gain at omega, but I am also getting a pesky term of 2 omega, which means I put in a sinusoid at omega. I am getting higher amplitude of that desired sinusoid, but something else has crept in, right? Exactly, right? So his point was in nonlinear source, if I can control the nonlinearity, which means if I can control eta, right, then it's possible that I can control this to whatever desired amplitude I want it to be, right? So I can in principle, I should be able to suppress this 2 omega component. Okay, but note that you cannot get away from the fact that there will be a 2 omega component. And note that here again, I have only assumed that you have a second order nonlinearity, right? This is just one of those toy systems that I use to make the point. It's not necessarily your circuit will have only second order nonlinearity. It can have third, fourth, fifth, nth order nonlinearity also. So these extra nonlinear terms creates distortion of your signal. And note that how does this distortion vary with the input amplitude? In this particular case, if you increase the input amplitude by, let's say, 10%, the output amplitude will also increase by 10% for the linear term, right? But can you comment on how the distortion term is getting affected because of increase of amplitude? Okay, so let me sketch and show it maybe. So what are you getting? Your input is, the signal input is a sinusoid, right? This is T, this is V, this is input. What are you getting at the output? You are getting some DC. On top of that, you are getting an increased amplitude of your sinusoid. So let's say this is 1 milliseconds, this is 1 milliseconds. And you are also getting a, I think I messed up the sign here, it will be minus. But anyway, you are also getting a cosinusoid, which is at double the frequency, which means you will have, this is 0.5 milliseconds, so you will have one cosinusoid at okay. So this stuff will make your hearing experience uncomfortable. Right? This is a high pitched voice, rather, if you think of in terms of audio. Right? So I am speaking at, let's say, 1 kilohertz, you're getting something at 2 kilohertz also, which is a shrieking voice that you sometimes hear if you crank up your volume. So that essentially, now comment, what I'm trying to get at here is that, can you comment on if I increase this input VP from, let's say, VP to 2 VP, right? So if I increase this input VP to 2 VP, comment on the amplitude of the desired sinusoid at the output. It will increase, stay the same, or decrease?
Become twice.
It will become twice. It will simply become twice. It will linearity, right? So this will simply become twice. Sorry. So this will simply become twice. What about the component with 2 omega? It will become 4x, right? So looks like the distortion component, the undesired frequency component, is running faster than my desired frequency component if I increase the input amplitude. That is happening because it should not surprise us, because I have squared. This distortion component has come because of a squaring operation, which means if I increase my input amplitude by, let's say, 1 dB, the distortion will go by 2 dB. Whereas the desired sinusoid will go by 1 dB. So that is why if you take any nonlinear system and if you crank on the input, you will see that the distortion, the effects of distortion, whatever it might be in terms of audio experience, it might be the shrill extra voice that you don't want to hear. Those things come up as you keep on increase the amplitude. If you turn the volume, you will get higher and harder distortion. Yes.
Can you please explain the scaling of distortion?
Okay. So why don't you tell me? So let's assume that the input VP has gone in by factor of 2, right? So what do you see at the output? You get this linear term that goes by factor of 2. This is the undesired term. This goes by factor of
1.
why?
Sorry.
If it,
Trigonometric term.
no. So what is the coefficient of sine omega t? So coefficient of sine omega t is what? So let me just write it here. So you have a sine omega t term, and you have some coefficient, let's say a times VP. Right? What is A? A is everything other than VP here, right? So this goes by, if VP increases by 2x, A times VP increases by 2x. Okay? So now, if you see the undesired term, right? If you see the undesired term, then what do you see? You get cosine 2 omega t, and you have something which is maybe B times VP squared, right? So if VP increase by 2x, what does B VP squared do? It increases by 4x. That's all the point is, right? So your undesired stuff increases, you make your system louder, right? And it increases at a faster rate. And it's quite possible that if you keep on cranking up, this undesired component might catch up and become the dominant one. So essentially you get junk at the output. So that is why in nonlinear system, you will see that there is a lot of effort in keeping this amplitude down. you will see later on why, I mean, you cannot keep the amplitude down across the circuit. There are certain parts of the network where there will be effort to keep the amplitude down because of these reasons. Okay, it's not necessary that the amplitude need to be smaller at all portion of the circuit, because that will defeat our purpose. Ultimately, we want to handle realistic signals. And you have seen from your experience that your cell phone works, right? Your audio player works, even if you shout at it, I mean, with fairly strong voices, right? So they work, which means there are ways of getting past this problem of increasing amplitude gets you more and more distorted output. The key to that is to figure out there are some specific parts of the network where I can afford to increase amplitude, and there are some specific parts where I cannot afford to increase amplitude. So those will be the parts of discussion in this course going forward. Okay. So to summarize, you need non-linearity. You need an extra power source to get power amplification. However, it comes with a cost, and the cost is distortion. But in order to reduce distortion, we can do something. What we can do, I haven't really talked about. We can do something, and we will see that going forward. Right? Are you convinced?
So if we
Yes.
apply the low pass filter at the output, then
One of those things, right? His point is, if I apply low pass filter whose cutoff frequency is between omega and 2 omega, then I can get rid of 2 omega, right? That in fact is one of the uses of low pass filter. That is in signal processing, that is one of the uses to get rid of undesired harmonics, right? Okay, fine. So now, if we are convinced that this is possible, then we have to see what, I mean, other than nonlinearity, are there any requirement? Are there any okay, let's take a generic nonlinear circuit now, system. Are there any attributes to this generic nonlinear system which can give us what we want? So let's assume this is again a nonlinear system. This is I1, this is I2. Note that this is total I1, total V1, not incremental, right? This is total I1, total V1. And since this is nonlinear, I can associate a nonlinear function between I1 and I2, between I1, V1 and V2, I2, V1 and V2. Okay. So generic nonlinear function, I can say that I1 will be equal to, let's say, F1 times F1 of V1 comma V2, and I2 is another function F2 of V1 comma V2. Okay. So now from the principles of, yes.
Dependent on I1 and V2. How can I1 be a function of V1 and V2?
Why cannot? I mean, let's assume that I have.
What are dependent?
Yeah, okay. So let's, I mean, it depends upon what are you driving it with, that makes it dependent or independent, right? So if I say that I have a battery, which is V1, I have a battery, which is V2, then you are good, right? Okay. So the reason you will see that we take voltages to, there is no mathematical reasoning as to why we should take voltages as the independent variable at the input port. In fact, there are cases where we drive circuits with current, but overwhelmingly you will see that most of the circuits that we drive are with voltage sources, not with current sources. So in general, we take voltages at the input ports to be the independent variable. Okay. So, but good question. Okay, so now we'll do exactly the same thing that we did with our diodes and those type of circuits, right? So what we'll say is that if we increase this voltage of V1 to V1 plus delta V1 and V2 to V2 plus delta V2, right? I'll use a different color maybe. Okay, so I would expect the output to increase by this currents to increase by some del y1 and some del I2. Okay, so now we have dealt with this enough to figure out how to evaluate these del I1s and del I2s, right? So let's do it one more time. So what will be I1 plus del I1 will be, help me out. And if I do a Taylor series of this, what will I get? Plus, yes. Don't be sorry to ask questions. Yes. Okay. Why? Okay. So let's assume. Let me take a simple. Right. Then you get what? The input current is dependent on V2, right? Same. So just you need a way of, okay, one can argue that in a simple resistor also there is a feedback because we increase resistance, but increase the voltage at one end, the current reduces, right? So what I essentially am getting at here is that there is, in a generic format, you cannot really say that the current at one port is only dependent on the voltage of that port if the circuit is interlinked. Right? This essentially says that all parts of the voltages of the circuit is affecting all other parts. And that's the most generic form, which means that any current that I observe will be a function of voltages at all the available ports. That's all this function means. Okay, so now if I expand this in a Taylor series, what do I get? I get delta V1 differential of F1 around V1, V2 plus delta V2 differential of F1 around V1, V2. Okay, thank you. So we know partial derivatives, right? So this will be del F1, del V1, right? Around V1, V2. And this will be del F1 by del V2 around V1, V2. And you will have bunch of other square terms, V1, V2 terms, and so on, right? And we have dealt with this sufficiently enough to say that we'll keep our distortion low enough, or we'll keep our delta V's low enough to neglect those terms, right? Okay, now what is the next step? If I'm interested in only the deltas, if I'm only interested in the increments, how do I get the relationship between the increments? I subtract this equation, this from whatever we are getting now, right? So essentially we get, so this is 1, this is 2, this is 3. So 3 minus 1 gives us delta I1 will be equal to V1 okay. Similarly, I'll get del I2 will be equal to, I'll not go through the steps, but essentially you can just look at it and tell me it will be del V1, del F2, del V1 around the quiescent points of V1, V2 plus del V2, del F2, del V2 around the quiescent points of V1, V2. Does that make sense? Okay. So now, if I look at these equations, so even going forward now, since we are comfortable with replacing deltas with small, the notations that we have been using, we are trying to using. If I say del I1, I can replace this del I1 as small I subscript 1, and similarly, small delta V1 can be replaced as small v subscript 1. So this becomes del F1 del V1 V1 plus del V2, V2. Similarly, this becomes del I2 equal to del F2, V1, 1, del F2, del V2, V2. Okay. So have you seen any, I mean, in your past courses, have you seen any set of equations, any other past, I mean, ESC 201 or even E 200, have you seen a set of equations, any circuit that corresponds to this set of equations? No? Have you seen Y parameters, Z parameters?
Yes.
Yes, two-port networks you have, right? So what can I mean, if I express this in matrix form, what do I get? I get I1, I2 is equal to right? So this essentially what is this telling us? This is essentially relating the incremental, it is relating the incremental input voltages and the incremental input currents, or rather it is relating the incremental currents at both the terminals of my nonlinear two-port network with a linear relationship, right? I got rid of the nonlinearity by simply subtracting the quiescent, and I retained only the first order terms. So I'm getting a linear relationship between a set of linear equations that relates I1 and I2, incremental I1 and I2 with the incremental V1 and V2. And what is this matrix that relates I to V called? Any comments? No, I mean in terms of Z parameters, Y parameters, H parameters.
G parameter.
Not really. Z is what? Z is impedance, right?
Admittance.
It's an admittance matrix, right? It's called Y parameters. So this essentially, okay. So if you don't know this, let me refresh your memory a bit more, or you can also go and look it up. So a generic two-port network. So let's assume this is a generic two-port network. By the way, why do I call this two-port? Because it has two ports, right? So which means that I have V1, I1, I'll have V2, I2. I should be able to relate V1 with I1, I1 with V1 and V2, and I2 with V1 and V2. That's what we did at the first step. But now what I am asking is that what is this? When I do this, right? So even if I go right in the beginning, okay, let's stay here. So what will be the unit of these del F del V's? It will be that of 1 over R, right? It will be that of admittance, right? And how do you generally, had it been a relationship between V1 and I1, right? I could have as well, coming back to his question, I could have as well started off by saying that V1 is the dependent parameter, I1 is the independent parameter, and I could have said that I could have formed a similar relationship of V1 equal to, I don't know, maybe del G1, del I1 plus del G2, sorry, del G1, del I2. Similarly, V2 equal to something times I1 plus something times I2. I could have done that. So if we would have done that, what would have been the units of these differentials? Impedance. So impedances we denote normally by Z or Z, and admittances we denote by Y. So whatever matrix you get by doing this is called the Z matrix, Z matrix, and whatever whatever matrix you get with this is called the Y matrix. And these parameters, that is differentials, in this case it's differentials because we are interested in incremental, but essentially you can you can write a set of equations that relates any I with any V in this matrix form, right? It need not be incremental per se. And the relationship that governs the matrix that governs the relationship between I and V is called a Y parameter matrix. Okay, so these are incremental Y parameters, right? These are, let's write it again. So I1, I2. These are called incremental Y parameters. And as it turns out in the literature, even going forward, we will not refer to these dels and dels and dels repeatedly as is. So there are terms which we replace them with. We say that the first term del F1, del V1 is Y11. That is, it relates so this Y11 and Y, these two subscripts, Y1, two subscripts essentially refer to the ports, right? So let me write it down, then it will become clearer. So this becomes Y11, this becomes Y12, Y21, Y22. So essentially what I did, I replaced those del F terms with a nomenclature, and there's a reason the nomenclatures are like these. So this, if I expand it, so let's look at to make the point. What I'll do, let's look at only this term. So this clearly, I am trying to. What does this Y21 imply? This Y21 is implying, it's trying to establish a relationship between the input port and the output current, and the subscript 21 is referring to the ports between which I am trying to establish the relationship, right? So 2 here, the first subscript refers to the output side, the port that I am interested to observe, and the second subscript refers to the port at which I am applying the excitation, right? So that's essentially the nomenclature. Have you done this ever? So this was ESO 203 stuff, not ESC 201 or okay. Then maybe I'll have to go back and refresh your memory from the next class on this a bit more. So okay, so essentially, so till now, are you convinced that I have not done any cheating here? So this is okay, right? I have not pulled anything out of the hat. This comes from first principles, right? Okay, fine. If you are interested, if you are convinced on that, then I would say that I'll then provide some material on this 2-port network. This was not a part of my plan, but this is essential. So I'll provide some material. You can go through it. So essentially, to recap, you can establish a linear relationship between incremental inputs, incremental voltages that you have applied at the ports and the incremental currents that you are observing, and the matrix that correlates that relationship is called Y parameter, incremental Y parameter matrix. And the reason it's called Y parameters should be obvious, because their units are that of conductances. Now note that this, if I now concentrate on this particular equation only, what does this tell you? This is essentially telling you that the relationship between I1 and V1, V2 are not only linear, but look at only this term. If I only concentrate on this term, which means that how do I concentrate? If you are doing an experiment, how do we concentrate on one particular term? which means you have to desensitize the other term. How do you desensitize V2 in an experimental setup? You keep it incrementally 0, which means you have to keep it constant, right? You cannot change its operating point. If you change its operating point, you are changing these parameters. These differentials will change. Because y11, y22 are differentials. They are differential. The slope of the curve around operating point. If you change your operating point, the slopes will change. Thereby, y11, y12, y21, y22 will change. So you cannot do that. So when I say I have setting this small v2 to 0, what I'm saying is that I am pinning down the circuit on its operating point, which means if I have a voltage source, constant voltage source, I have to keep that. I'm not adding any incremental. I'm not adding any extra maybe sinusoid. But I am adding that extra sinusoid at one port, one of the ports. In this case, I'm applying the sinusoid at V1. Right? So if I do that, if V2, small V2 goes to 0, what do I see? I see I1 is equal to Y11 V1. So this is a linear relationship between I and V. So what does this element look like? It's a resistor, right? Having a conductance of Y11. So essentially, if I observe the port V1 and I observe the current I1 and I incrementally short the port V2, the current that I will see will behave like it's going into a resistor of value 1 by Y1. Right? This is incrementally shorted, right? So in a real sense, what I am doing, if you have a V2, in a total sense, I have a V2. In a total sense, I have a V1. On top of that, I am applying a V1. Right? So there you will get I1 plus I1. Here you will get I2, only I2 plus some I2 you will also get, right? But just that I'm pinning this voltage down, the incremental equivalent of this network is the network on that. Right? Okay, fine. We'll meet on Wednesday.